Section 2.4, the normal distribution. This section we're going to look at the empirical rule, and then we're going to use z-scores to determine if values are unusual. The normal distribution itself is a very common distribution in statistics. And if you were to go on and take another stat class, you would see lots of things that deal with the normal distribution. It's one of the key distributions for an intro to stats. So, you see a lot of different things done with it. We're going to touch on some of those here, but we're not going to go anywhere near the depth into things like what you use the empirical rule for. There's other approaches to get more exact values that we just won't be doing in this class. It's just not in the scope of it. But the normal distribution is a very important part of statistics, and we're just going to kind of get a little bit of the flavor of it here, of what you can do with it. So the empirical rule, looking at this first. Earlier we looked at histograms and talked about their shapes. And one shape that shows up often in statistical distributions is unimodal and symmetric. And I think I mentioned this in that section, that we'd be seeing this again. And just to refresh that shape, it's something like that. So this distribution shows up so much that's given a special name, normal distribution. And you would see, if you were to take a whole bunch of data from the heights of people and then form a distribution, a histogram with that, it's going to have a unimodal symmetric shape. If you went out in the forest and measured all of the heights of a similarly aged type of tree, you would see that it forms a normal distribution. So many things in nature, when you measure certain characteristics of them, end up forming a normal distribution. That's because, nature, you've got a lot of stuff that's kind of common that forms that, kind of the bulk here, the bump in the unimodal symmetric shape. And then you have some outliers on the low end, outliers on the high end that, give you the tails on both sides. And typically those tails are pretty much about the same size out there. You have about the same as many that are going to be lower than normal and same as many as are going to be high as normal. So that shows up all over the place in especially nature characteristics when you start measuring them and putting them into histograms. So that's one of the reasons why statisticians are so enamored with it. It shows up all over the place. Now, a key fact about the normal distribution is that the mean, median, and mode are all equal. And I mentioned this in another section as well, but just to bring it back to the forefront. Oops, sorry about that. So, you got your normal distribution right there at the peak. The mean equals the median equals the mode. And that'll always be true in a normal distribution as well. And another key fact is really how much of the data is located within 1, 2, and 3 standard deviations of the mean. And this fact is true for every normal distribution. And this is what leads to the empirical rule. So basically, if you're given a data set that is approximately normally distributed, approximately 68% of the data is within 1 standard deviation of the mean. Approximately 95% of the data is within 2 standard deviations of the mean. So you go out 2 standard deviations away from the mean, and you've captured most of the people, almost 5% short of being all of the people in your study or in your population. And then approximately 99.7% of the data is within 3 standard deviations of the mean. So you go out 3 standard deviations in a normally distributed data set, whether it's population, whether it's sample, whether it's people, objects, whatever you're measuring, if it forms a normal distribution and you set it up, 99.7% of the data is going to be within 3 standard deviations of the mean. So very few objects or people beyond that. And visually, what you'll see here in this normal distribution, if you want to think about this, 68% of the data is within 1 standard deviation of the mean. So the mean here would be right in the middle. And then if we add 1 standard deviation and then subtract 1 standard deviation, 68% of the data is going to be between these 2 lines. So the bulk of it is within 1 standard deviation. This is something I alluded to when we talked about the spread. Standard deviation, one of the meanings for this average distance away from the mean, is that if they tell you the standard deviation, you add it, you subtract it from the mean, you know that more than half of the data is within there. And in this case, when it's a normally distributed data set, 68% roughly is between there. So this bar in the middle here splits that 68% into 2 equal parts. So you got a 34% here and a 34% here. And this is important because we're going to see later on, having these individual percentages filled into these different regions is going to help you answer questions. So that's why we're doing this. 95% within 2 standard deviations. So we'd have sigma minus 2 over here, or I'm sorry, mu minus 2 sigma over here, and then mu plus 2 sigma over here. So in between these 2, you're going to have 95%. So we had between these 68% total. And let me scroll down a little bit more now. And then between these 2, oops, it should be blue now. So between these 2, you got 95% of the data. And in order to figure out what goes into these little pieces here, I'm going to take the 95% that I know is between the 2 standard deviations, subtract away the 68% that's already there, and you're going to get 27. Now that's going to get split evenly into these 2 different parts here. So 27 over 2 will give you 13.5. So it's going to be 13.5% here and 13.5% here. And then last but not least, come out here, and now we've gone 3 standard deviations. They usually don't go beyond this because there's so little out there. If you go out 4 standard deviations, you're maybe going to capture another point something percent, but technically these little tails go on out to infinities, to account for all the possible crazy outliers. So they just focus on 3 because at that point you've almost got 100%, so it's not really too necessary to go out to 4. But at any rate, oops, I'm writing 100% there, but this should be 99.7. So 99.7% within those 2 red lines there in your data set. And again, I'm going to do a similar idea here. I'm going to take 99.7 minus 95 and trying to figure out what goes into the 2 missing regions. And this is going to be 4.7. When you divide 4.7 by 2, you get 2.35. So in here is 2.35%, and in here is 2.35%. And then you, last but not least, have 100% total, in theory, underneath this curve. And it's always, if you've collected all of the data, if you've collected a census, you do have 100%. So beyond that 3 standard deviations, you would have basically 0.3% left over. And then you divide that by 2, and you get 0.15. So in here, and I'm going to draw this up this way. So you got 0.15% here, and over here you've got 0.15%. And you might be saying, gosh, that sounds like a lot of work. Why do you got to do this? Again, in these problems that we're going to be doing, you need to draw this picture first, and then you'll use the relevant numbers that are given to actually write in the number for the mean, the number for mean plus standard deviation, mean plus 2 standard deviations. You actually write numbers down here. And then when they start asking you questions that they like to do with the empirical rule, you'll have the percents right at your disposal. These percents will never change. So if you remember 1/2 of it, you can fill in the other half because it's symmetric. So it's always going to be 0.15%, 2.35%, 13.5%, and 34%, and then decreasing that same, using the same numbers on the other side, mirror image. So the only thing that's going to change are going to be these numbers down below, the means and standard deviations based on the problem they give you. But if they tell you it's normally distributed, the percents, again, will always be the same. So let's go ahead and take a look here. We're going to use the facts that we just saw about that normal distribution to answer some questions. So we had 4,100 students taking a standardized test in a local school district. The mean score was 630. So right there, that tells me, okay, there's my mu. And then standard deviation was 35. Okay, I got that. Assume the data are normally distributed, round to the nearest integer. So before I even go down into A, B, C, D, and E and answer these questions, and this is what I expect you to do if you want to get this right the first time, draw out a normal distribution, put in the marks for the 1, 2, 3 standard deviations away. This first standard deviation, you can kind of see when I draw this, it's kind of like a lazy S here. And right here you got like cupped up, and down here you got cupped down, or I should say cupped down, then cupped up. But where it changes from cup down to cup up, or as they call it, concave down to concave up, it's an inflection point. And 1 standard deviation away is in a normal curve at that inflection point. So that's how I know how to draw it there. And then I just kind of space it out evenly for the rest, going out here and then out here. So what I want you to do is pause this video, use the mean, use the standard deviation that was given, and fill in the bottom with the numbers, and then fill in the percents that are supposed to be there. So go ahead and do that. Okay, so you should be seeing a picture like this when you're done. You got the 630 right in the middle, because that's the mean. And then I added 35, the standard deviation, to that, and got 665. I added 35 to that to get 2 standard deviations away, or up to 700. And then I added 35 to that to get up to 735, or 3 standard deviations away. And then I just subtracted on the other side. So 630 minus 35 gave me 595. Subtract 35 again, and you get 2 standard deviations of 560. And then 35 subtracted from that will give me the 3 standard deviations away on the low end, 525. And then all those percents that we saw earlier should be filled in as they are. So now I should come down in here. You can use this to answer the questions. So go ahead, pause the video, and answer the 5 questions that follow. I'm going to go ahead and put the answers to this in part 2.